Hi, and welcome to the video on cross multiplication. I want to talk about two things here, which is how to use this tool in algebra and also why it makes sense. So let's start up with a string to understand why this makes sense, or at least one way to think about why this makes sense. So I'm going to build a bunch of fractions that are equivalent to 1/2, right? 1/2 is equal to 2/4. I'm going to keep going. Here, I multiply both numerator and denominator by 2, so I'll do that again, right? So here, this will be 4 over 8. And then we'll keep going. We'll keep doubling everything. We'll get 8 over 16. And these are all equivalent, right? 16 over 32 and 32 over 64. 64. 32 over 64. How does this relate to cross multiplication? Cross multiplication points something out that's quite useful, which is that if you multiply across here for these two fractions, you might notice something. Actually, let me use a different color. If I multiply these two, that's 2 times 2, and that's 4. What happens if I multiply these two? 1 times 4 is also 4. So here are two equivalent fractions. If you multiply across, you get the same value. Let's try that again. Over here, right, 2 times 8 and 4 times 4 are both the same number, right? 2 times 8 is 16, and 4 times 4 is also 16. Keep going. Here we have 4 times 16 and 8 times 8, and of course, they both equal 64. So one thing you should notice right now is that when you have these equivalent fractions and you multiply across, you're always going to be getting the same value, right? These both equal 256, and I'll write those equations out, sorry. 8 times 32 equals 256, and 16 times 16 also equals 256. And over here, right, our last one, here we have 16 times 64, and 32 times 32. What's 32 times 32? Well, I'll set that up here, or down here, sorry. Just do a quick long multiplication problem. 2 times 2 is 4. 2 times 3 is 6, right? We have a 0 now because we're multiplying 30 by 2 to get 60. 30 times 30, 900. Add this up. I'm running out of room. We get 4 to 1024. So this is 1024. And so is this. And now the point is, these fractions are equivalent, so you can multiply across and you'll get the same values. But we can also mix things up. What if I took 1/2 and not 2/4, right? Because maybe that's too obvious for you because this 2 is up here and it's been repeated from this denominator. What if I grab this one over here? Let's compare these two. 1 over 2 is equal to 8 over 16, right? They're all equal to each other. But if we cross multiply, here we have 2 times 8 and 16 times 1. 2 times 8 is 16. And 16 times 1 is 16. So it's still equivalent. This concept right here is at the heart of cross multiplication. What ends up happening, and I'll clear this off. Let me use this little space up here. What ends up happening with cross multiplication is you use this observation that multiplying across is equivalent to solve for x. So for example, let's say you have x, right? And it's in a fraction. So we have x over 6. And we know it equals another fraction. Let's say 5 over 9. Right? What's going to happen here? To solve for x, we could realize immediately that we have two fractions that are equal. Fix this. So what we can do is say that this product will equal this product, right? So 9 times x will be the same as 6 times 5. And now we have a simple equation to work with and solve. So here we can divide both sides by 9, and this is we're divided by 9, and that's really 30 divided by 9, and that's what x is. Of course, it can simplify. 9 times 3 is 27, so 9 goes into 33 times, with a remainder of 3, or 3 out of 9. And that's just 3 and a third. So what we did was we used this observation that multiplying across makes two equivalent expressions, right? And then use it to solve for x. Let's look at a couple more examples. So again, I can put x in the numerator here. Let's put a 3 here now. And then let's put, I don't know, a 5 and a 6 over here. What do we do to solve for x? There are many ways to do it, but using cross multiplication, we know that this product will have to equal this one. So we get 6 times x equals 3 times 5. Simplify this, it's 15, and 6x equals 15. Divide both sides by 6. These cancel out. 6 goes into 15, right, twice, with the remainder of 3 out of 6. Or, really, you can think of this as just 2.5. So this works, right, when solving for x. And another way of looking at this, if we flip things around, what if we had 4 over x equals 8 over 9? What do we do? Sometimes I see that people really get bogged down just to think about where the x is, right, in the denominator or numerator. But you don't have to worry about that too much, because really what you're looking at is that this product, 8 times x, is equal to this product, 4 times 9. That's the goal. So don't worry about how to get this out of the denominator or how to get in the numerator. Just remember that the products that are across like this, using cross multiplication as a tool, we know they're equal. So here, let's simplify. 4 times 9 is 36. And 8x equals 36. Divide both sides by 8. Okay, here we go. 36 divided by 8, that's 4, right? Because 8 times 4 is 32. And there's 4 out of 8 left over, or 1/2. So this actually equals 4 and 1/2. And this is the basic idea in cross multiplication. Another way of looking at it is to look at it in context of balancing both sides of an equation. Because sometimes I think what ends up happening, we set this up, x over 4 equals, I don't know, 5 over 7. Sometimes when we cross multiply, we forget really what's happening in the background here in terms of balancing equations. Remember that in algebra, whatever you do to one side of the equation, you have to do to the other. So really, even though we know that this product equals this one, there's more to what's happening here than just saying 7 times x, and that equals 4 times 5. How are we really getting from this step to this one and still keeping everything balanced? What's going on? Let's rewrite it, and I think we'll see. So x over 4 equals 5 over 7. Okay, so to multiply 7 by x, I really can't just multiply across like that. I can using the technique of cross multiplication, but what's that based on? It's based on inverse operations, right? If I wanted to multiply this side by 7, I also have to multiply this side by 7. Now, you don't show this typically in cross multiplication, but this is what's happening in the background, so to speak. Because here, if we're dividing by 7, right, this line with a 7 here means divide by 7, and then we're multiplying by 7, this cancels out to 1. And in that way, we can now multiply 7 by x to get 7x. And the same works for the 4. I'm not just multiplying 4 by 5 and that's it. I'm multiplying both sides by 4, right? Because here, eventually I'll be multiplying and dividing by 4 on the left side. But on the right side, I'm multiplying 5 by 4 to get 20. So we're still balancing everything in the equation as we do for other algebra problems. Cross multiplication is a shortcut in the sense of what we write, but it's still keeping everything balanced.